The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let me remind you, yesterday we've defined and started to compute line integrals for work of a vector field along a curve. Okay, so we have a curve in the plane, C. We have a vector field, F, that gives us a vector at every point. And we want to find the work done along the curve. So that's the line integral along C of f dot dr, or more geometrically, line integral along C of f dot t ds, where t is the unit tangent vector and ds is the arc length element. Or in coordinates, that's the integral of m dx plus n dy, where m and n are the components of a vector field. Okay? So let's do an example that will just summarize what we did yesterday, and then we'll move on to interesting observations about these things. So here's an example we're going to look at now. Let's say I give you the vector field yi plus xj. So it's not completely obvious what it looks like, but here's a computer plot of that vector field, so that tells you a bit what it does. Points in all sorts of directions. And let's say we want to find the work done by this vector field if I move along this closed curve. I start at the origin, then I moved along the x-axis to 1, then I move along the unit circle to the diagonal, and then I move back to the origin in a straight line. Okay, so C consists of 3 parts. So that you enclose a sector of a unit disk corresponding to angles between 0 and 45 degrees. So to compute this line integral, well, what we have to do is we have to set up 3 different integrals and add them together. Okay, so we need to set up the integral of y dx plus x dy for each of these pieces. So let's do the first one on the x-axis. Well, one way to parameterize that is to just use the x variable and say that because we are on the, we're going from the origin to 1, 0. Well, we know we're on the x-axis, so there's y there is actually just 0, and the variable will be x from 0 to 1. Or if you prefer, you can parameterize things, say x equals t for t from 0 to 1, and y equals 0. What doesn't change is y is 0, and therefore dy is also 0. So in fact, we're integrating y dx plus x dy, but that becomes, well, 0 dx plus 0, and that's just going to give you 0. Okay, so there's the line integral here is very easy to compute. Of course, you can also do it geometrically, because geometrically, you can see on the picture, along the x-axis, the vector field is pointing vertically. Right? If I'm on the x-axis, my vector field is actually in the y direction. So it's perpendicular to my curve, so the work done is going to be 0. F dot t will be 0. Okay, so f dot t is 0, so the integral is 0. Okay, any questions about this first part of the calculation? No? It's okay? Okay, let's move on to a more interesting part of it. Let's do the second part, which is a portion of a unit circle. Okay, so maybe I should have drawn my picture. And so now we are moving on this part of the curve, that's C2. And of course, we have to choose how to express x and y in terms of a single variable. Well, most likely when you're moving on a circle, you're going to use the angle along the circle to tell you where you are. Okay, so we're going to use the angle theta as parameter, and we'll say, well, we're on the unit circle, so x is cosine theta, and y is sine theta. What's the range of theta? Theta goes from 0 to pi over 4. Okay? So whenever I see dx, I will replace it by, well, the derivative of cosine is negative sine, so minus sine theta d theta. And dy, the derivative of sine is cosine, so it will become cosine theta d theta. Okay, so I'm computing the integral of y dx plus x dy. That means I'll be actually computing the integral of, so y is sine theta, dx, that's negative sine theta d theta, plus x is cosine, dy is cosine theta d theta, from 0 to pi over 4. Okay, so that's integral from 0 to pi over 4 of cosine square minus sine square. And if you know your trig, then you should recognize this as cosine of 2 theta.